Sure, why not? Let's start with a round of applause. I haven't done anything yet, but why not? Let's go. Okay, good morning, everybody. So today I'm going to be talking about machine learning in healthcare. Why my radiologist is not yet an algorithm. So just always helpful, I think, to start with an outline. So I'm going to start with the hype surrounding radiology and AI, the reality underlying that hype, going through two examples, and then we'll talk about the limitations of current AI algorithms in radiology, and then ending off with the future of radiology and AI, ending on a more positive note, as hopefully you'll see. So, give a second to read the comic. I think this is a relatively apt comic for the hype surrounding machine learning and artificial intelligence these days, right? You just throw enough data in there, mix things around, and eventually you get something that looks good. So here, I just want to go over some of the headlines I've been seeing for the past couple of years regarding artificial intelligence and radiology. So this is a piece by The New Yorker, this very antagonistic relationship between artificial intelligence and doctors, a piece from VentureBeat about this unanimous AI swarm technology that does 22% more accurate pneumonia diagnoses. MIT's AI can identify breast cancer risk as reliably as a radiologist. From the BMJ, could artificial intelligence make doctors obsolete? From NPR, radiologists see their futures at risk. From Fox, about AI and Alzheimer's, that it's 6 years better, or predicts it's 6 years earlier than doctors do. Even the New England Journal of Medicine is getting on this with an opinion piece that machine learning will displace much of the work of radiologists and anatomical pathologists. And then from Andrew Ng, one of the leaders in the field of artificial intelligence, saying that they have an algorithm for diagnosing pneumonia from chest x-rays better than radiologists. So now we're not even as good as, we're now better than radiologists. And finally, finishing off with a quote from Jeff Hinton. This is about a 2-year-old quote, but I think it's very interesting. He's saying at the end that it's just completely obvious that in 5 years, deep learning is going to do better than radiologists, and we should stop training them now. Well, that's simple. I think that's pretty clear. So yeah, we're good. So let's talk about the reality. Is this actually true? And I think this is also cute. So I like XKCD, if you can't tell. And I think he has really great comics that really kind of sum up the field in general, right? That some things that seem simple might not be nearly as simple. So let's take a look. So this is the paper by Andrew Ng. This is the ChexNet algorithm which he developed at Stanford, and radiologist level pneumonia detection on chest x-rays with deep learning. So let's look at the claim. The claim is that ChexNet exceeds the average radiologist performance at pneumonia detection. So on the left, we have the radiologist task. On the right, we have the ChexNet. And they both are looking at a same radiograph. So this is a chest x-ray. We see the heart in the middle. And so the ChexNet is asked to do either a pneumonia or not pneumonia detection. So technically, this is actually a multi-class one versus rest task that was given. But we can think of this as a binary classification. Okay, you're given a radiograph. Does this have pneumonia or not pneumonia in it? The radiologists are also given a task. Not nearly as simple. They're told, hopefully everyone can read this in the back, but they're given 14 different diagnoses to work on. And there's actually a multi-label classification task. So an image can have anywhere between 1 to 14 different labels. So right off the bat, we're seeing that they're not really given the same task. The radiologists are given a much more complicated task to do than the algorithm. Additionally, when radiologists work, their workflow involves, you start off with not just a single image, but you're looking at the frontal view, the lateral view, and chest x-ray, and different imaging modalities will have different views. They also have a clinical indication. There's a reason why a patient had an x-ray taken. It's not just because, it's a Tuesday. There's something wrong with this patient or something hopefully getting better with this patient that's indicating an x-ray to begin with. And that is essential for any reading of an x-ray by a radiologist. And finally, radiologists are almost always given previous scans that tell them a fuller picture of what's happening with this patient. What was their scan yesterday? What was the day before that? How have they changed over time? This is how radiologists read x-rays. However, for this task, they weren't given any of that. They were given a single film without any other information and told, solve it. So it's like if I asked everyone here to run a race, but I'm going to blindfold you and tie your shoelaces together. We probably wouldn't do that well. And so it's not really surprising that this ChexNet algorithm, which is trained specifically on this one task, does better than radiologists who are doing a task they don't normally do. And then there's one more thing I want to really address, is just 3 of these terms. So infiltration, pneumonia, and consolidation. So there's a problem with these 3 terms, is that they all can mean the exact same thing. And so infiltration is actually an archaic term that is no longer really supposed to be used by itself when diagnosing or when reading films. pneumonia is a diagnosis, not a finding, and consolidation is an actual radiological finding. So another problem is that if the radiologist labeled it as a consolidation, they might be considered wrong because, hey, it was a pneumonia, not a consolidation, even though they can mean the exact same thing. So for these three reasons, I don't think this claim is actually as powerful as he'd like to make it seem. It's definitely a very interesting algorithm, and it is great at a single specific task of looking at chest x-rays from one view and trying to identify pneumonias, but I would definitely not call it better than radiologists. It's better than radiologists who are hobbled and given a much harder task. And so let's look at one more of these papers. So this is Deep Radiology Net, radiologist level pathology detection in CT head images. So the claim is that Deep Radiology Net missed less positive CT studies than radiologists, i.e. it had a lower false negative rate. So once again, let's compare the task of the radiologist and this Deep Radiology Net algorithm. So interestingly enough, they did not actually do a one-to-one comparison. Their measure of radiologist performance is actually based on a literature review. And so what they did was they said, okay, from the literature, we can estimate that there's an average error rate of about 1.2% for radiologists, and 68% of those errors, based on other papers they're looking at, are false negatives. So therefore, our false negative rate for radiologists is 0.083%, which honestly, that seems pretty low to me. So let's look at their Deep Radiology Net algorithm. What they did is they tested it on about 30,000 studies, which comes out to about 5 million images, which, as I'll come to a little bit later, is actually a really nice data set. Most people do not have nearly enough that much data to work with. But what they did was something very interesting. What they said is, okay, if we take the 8.5% of that data set on which our algorithm is most confident, it only has a false negative rate of 0.037%. That seems a little bit fishy to me. Right? Radiologists don't get the option of saying, well, I'm not really sure what this graph looks like, so I'm just not going to count it. But they're able to do that. They're saying, if we only take the ones we're most sure about, then we do much better than the radiologist. They then said, okay, but if let's say we take about half the studies, well, then we do pretty much just about the radiologist. And they don't actually report how well the algorithm does when it has to do all the studies. I'm assuming it does much worse than the radiologist. So, and once again, this is not a knock on their algorithm. It's probably a really good algorithm. I'm just saying, the data does not back up their claim that they're better than radiologists. If they cherry pick their cases, sure, they can do better than the radiologist who does not have that opportunity, right? But when they just have to work with the exact same amount of data that the radiologists have, I don't think they're even close to radiologist level performance. So the question now is why? What's so hard about medical imaging, or what's different about medical imaging than any other type of imaging, right? Because, I don't know, I've been told that machine learning or machine vision or computer vision is pretty much a solved problem. We can identify cats, we can identify dogs, we're getting self-driving cars. Why can't I do the same thing for radiology? So I think there's about four big limitations and differences between radiology and a lot of other computer vision fields, and then one other aspect that I'm going to discuss at the end. So I think it's about complexity, ground truth, quantity, artifacts, and then value add we'll come back to a little bit later. So first, let's talk about the complexity. So we have our standard chest x-ray, which is honestly one of the simplest of radiograph images to read. And then we have a koala bear, very cute koala on the right. So the first thing to notice, and I think the first thing I would notice, is the fact that the koala is in color, the chest x-ray is not. So already I've lost one dimension of information. So forget about the complexity, the task is already harder to do. Next, let's actually look at these images. This I do not think is a fair comparison, right? On the right, I have a single object I'm trying to identify. Is this a koala or not? Okay. For the most part, you know when you're seeing a chest x-ray. The question now is, what are the diagnoses inherent in the chest x-ray? What are those labels? So do I have cardiomegaly? Do I have a pneumothorax? Do I have flail chest? Do I have an infiltration? Do I have a consolidation? Do I have a pleurisy? Do I have, you can go on and on. There are literally hundreds of different findings in a chest x-ray compared to the one that I'm pretty much seeing in this koala. So I would call this an unfair comparison. If we want to think about what the natural image comparison of chest x-ray might be, or just radiology in general, something much probably similar to this. So this is, if you can see in the back, this is just a group of the Serengeti of wildebeest. And if I told you one of these wildebeest has a cold, tell me which one based on this image. I think that's a much more fair comparison, right? It's a much more complicated image, and I'm trying to find the 1 or 2 pixels that tell me, or that's different than the rest of the image, and it's different than hundreds and thousands of other pictures of similar wildebeest. Let's talk about ground truth as it applies to radiology. So I think there are three big issues in radiology. The first is going to be censored information. So there's a problem with a lot of these studies and algorithms. And the big issue is something called HIPAA, which if you're not aware of, it's what regulates medical imaging in the US and it actually or medical information in the US. And in case anyone ever wonder what it stands for, it's the Health Information Portability and Accountability Act. Everyone thinks the P stands for privacy. There's nothing about privacy in there. It's just about how we transmit information. But a big problem with that is that you can't give away patient information. And so radiographs are fine because there's no patient information in there. But a lot of other information does have that. So when a lot of these algorithms are built on these images, they have no other information but the image itself. So they're missing a lot of the information which would tell them the ground truth. I.e., let's say they have a lab test to diagnose whether it's pneumonia, a pathological finding, or something else that really can tell you what the image actually means. They don't have that information. And even if they do, the problem is it's in terms of labeling. Because when we talk about, let's say, the pictures of koalas or the pictures of self-driving cars, pretty much anyone can label that. That's the whole point of Mechanical Turk, right? Amazon can pay you 10, 20, 30 cents an image just to say, okay, it's a koala, it's a dog, it's a cute dog, it's not such a cute dog, right? But it's not really, you can't really do that with radiologists because radiologists are much more expensive for some reason. I don't know. I offered them 20 cents an image and they laughed at me. I tried. I offered them some cookies. No, got nothing. So what we tend to do instead is use natural language processing to extract information from the radiographs. However, the problem with, well, not just radiology reports, but medicine in general, is that medicine and radiology reports are not written for the purpose of research. They're written for the purpose of either clinical findings or for administrative purposes. And so there's not as much information in there as you'd like there to be. And then so let's say you have the information and you're able to do natural language processing on it and get everything out from it. Then there's honestly one problem I think exists in radiology which doesn't exist in a lot of other fields, is that there might not be one truth. There's this concept of inter-observer variability, that given 3 or 4 expert radiologists, they might all look at the same image and say completely different things about that image. And none of them are actually wrong because it's open to interpretation. It's much more of an art than a science reading radiographs. And so I think it's much harder to say what the ground truth actually is when trying to build these algorithms. So now let's talk about the quantity of images we can work with. So on the left, once again, we have our radiograph. On the right, we have our cute koala. So most of these studies, at least for the natural image studies, when we're looking at these natural pictures, we're talking on the order of tens of thousands or hundreds of thousands to tens of millions of images, which is what we kind of need to build these. When we're talking about medical imaging, we're usually talking about hundreds to thousands or tens of thousands, which is why I said that CT study was pretty impressive. But then once again, they only had 30,000 CTs. However, the problem is actually more dire than that because the classes aren't even. Right? When we're talking about natural images, you're usually talking about even classes. I have the same number of pictures. Well, I always have more pictures of dogs than everything else, but I have enough pictures of koalas. I have llamas. I can get enough of that data. In most of these cases, most radiographs are just normal. People are healthy for the most part. They do not have these diseases. So 10% positive is actually really high. We find usually about 1 to 2% positive cases. So now my 10,000 quote-unquote cases has now gone down to 10 cases. So I now have 10 positive cases from which to learn everything. And let's talk about the sources. And this is part of the reason why I don't have so many images, right? Anyone could go to the zoo and take a picture. You can't really just walk into an x-ray and say, okay, I'd like to take x-rays of the next 5 people. It's fine. Don't worry about it. I'll give you $20 on the side, right? It's not nearly as simple to get these images out. And a big problem with that, besides for just the medical issue, is the fact that there's just so much cost associated with medical imaging that just does not exist in other fields. So we have a lot less data. It's a lot harder to know the truth about it. It's a lot more complex. And then just to make things harder, because why not? Let's talk about artifacts. So on the right, this is from the Explaining and Harnessing Adversarial Examples paper that was published about, I think, 2 years ago. This is a great paper which is talking about how we train computer vision algorithms. And so on the left, what we have is a panda. And the model has a 57.7% confidence for it. If we then add a little bit of pixel noise to it, and we then look at it again, to us, or to me, it looks like a panda. I haven't seen any change in this image. However, the machine learning or the computer vision algorithm now believes with 99% confidence that this is a gibbon, which is a monkey, which is not really the same thing as a panda. And so the problem is artifacts in radiology are extremely common. So I'm not sure if the people looking in the back can see this, but on the left, what we see over here is, I have no mouse, but pretty much on the left, we're seeing something called a mirroring artifact, and then we have a texturing artifact. And these are very common in radiology just because of the way the technology is built. And they happen all the time. And for us, they're not really an issue. We can see very easily past these artifacts. But they exist all the time, and it's very hard for the machine learning algorithms to see past them. I mean, some theorize that maybe the machines are rising up a little earlier than we predicted, but who knows? I just think, and forget about pixel noise. Pixel noise exists in all of these images. So we have, images are more complex. We don't know what they actually mean. We have less images. We have a lot less images than we have otherwise. And there's just artifacts that exist within them. And I think there's one more thing I want to talk about. So if we look at the automobile industry, right, there's not just self-driving cars. We've been using artificial intelligence in all the auto industry for years now, right? Everything from Google Maps to lane assist to fraud detection for insurance claims, to monitoring the car systems, to a couple years, I think it was a year ago, right? They were trying to build better cars, design better cars using deep learning algorithms. Every aspect of the auto industry is infused with artificial intelligence. And I think the problem is we have a tool. We have computer vision algorithms which can identify pictures. And we said, what can we apply it to? And I think that's very short-sighted because there's so much more to radiology than just images. And I think the problem is we're not seeing what else we can add. So I went and asked a couple of radiologists what they actually need help with. Not just trying to guess at it or do it myself. I asked them what they need help with. And this is some of the responses I got. One, they want to flag cases that are technically poor and need to be repeated. So this is a computer vision problem, but one that most people aren't really working on. There are a couple of companies and a couple of groups, but very few. Just saying, hey, this is a bad study. Repeat the study. Or patient scheduling efficiency, right? On average, every % of patients who miss appointments cost hospitals and medical systems about $1 million each every year. So if you can just reduce the amount of patients who miss appointments, you're saving the hospital millions of dollars. Prioritizing exams containing emergent findings. So this is something also a computer vision algorithm can work on, right? If something's new or different for that patient, not just different compared to the normal x-ray, but different compared to the patient's previous one, that's something that's really interesting. And providing better image quality with lower dose or shorter scan time. So you don't have to sit in the MRI in that really tiny space for 40 minutes would be really nice. Maybe we in and out within 5 minutes. Because the big problem with these studies is also MRIs take a long time to work with, a long time to do. And if we can get them done in half the time, that's a great value add. And I think the problem is, one of the big problems in artificial intelligence is that we're not looking at these other issues. We think we know what, like we're coming at this with this hammer, with this solution, trying to find a problem versus the other way around. So now that I've kind of depressed all of us, let's talk about the future of artificial intelligence in radiology. So I think once again, XKCD has a great point on this, right? Right, that's so great, all the captures, right? So that so much of AI is just figuring out ways to offload work onto random strangers, which I think is a great point. So here's what I think the future of radiology, and artificial intelligence in radiology, and honestly all of clinical medicine lies, is in these integrated clinical data science teams within hospitals. So you have at MGH, you have, this is on the top right, that's Stanford's, Hopkins, Duke, Mount Sinai. So I'm part of the Montefiore Health System, which is a system of 11 hospitals serving the Bronx and Westchester in New York. We have our own Center for Health Data Innovations. And so what I'd like to now do at the end, for the end of the presentation is talk about 2 different projects that are currently going on, one by us and one by MGH, which I think highlight the way we can do radiology and artificial intelligence. So the project I'm working on is called spinal cord compression. So when patients have cancer, that cancer can spread to other parts of the body. That's termed metastatic cancer. One of the places it can commonly go is the spine, which if it then expands, it presses on the spinal cord and can cause permanent lower limb paralysis, shooting pains, and loss of bowel and bladder control. So radiation oncology department came to us and said, help, we need help with this problem because if we don't diagnose these patients as early as possible, they will lose the ability to walk permanently. So hopefully you can see this. On the right is a normal spinal canal. And so we're looking at the side view where here are the different, here left the vertebrae, and on the left side over there is a patient with spinal cord compression. And you can see that there's a very much wavy pattern. That is an unhealthy spine. And so what we did is we started with about 70,000 spinal MRIs. And we took from them all the radiology reports, the clinical finding, and the clinical notes. We then applied this, passed this through a natural language processing pipeline using machine learning. and we came out with these spinal cord compression cohorts. Now, these aren't extremely accurate. These are only mostly accurate because this is a weak learner. But the nice thing about this is we do have radiologists on staff. So pretty much we bug them on their nights and weekends to label our images for us and say, OK, is this image have spinal cord compression? Does it have cancer? Is it normal? We've also picked a project in which there is a ground truth, because there are radiological findings which are pretty much standardized across the industry. We then pass it through a CNN, and I'm going to be a little bit vague about what algorithms we're using because it's not really ready for prime time just yet. And we're able to get spinal cord compression identification. This then goes through perspective validation. That's the nice thing about working with the hospital, is we can now run this in real time without actually implementing anything and just checking, are we catching the cases before the radiologists are? And then eventually our goal is to integrate this with the radiology tech stack. Because we're working really tightly with the hospital, they're ready for us to implement it the second we have validated that study. And then just one more quick study. This is a deep spine. This was a paper put out by MGH, Center for Clinical Data Science. So their issue they were working with was spinal stenosis. Apparently, spine is the new hotness in imaging. So if we look, what they're looking at is something similar, but actually a quite different etiology, is they were looking at spinal canal stenosis, so that's narrowing of the spinal canal, and how they can automatically grade their radiological images, because they just go through so many of these a day, and their radiologists are getting backed up on these images. So what they did is they have about 7,000 lumbar MRIs. They took out all the radiology reports once again. They passed it through an NLP pipeline, and they got disc level grading, i.e. at every level of the vertebra, they were able to pull out the associated finding. Once again, they chose a problem for which there was a relatively straightforward solution. Then concurrently, what they did was they had their radiologists go and label the images themselves and identify the edges of the vertebra. They then passed that through a UNet to pull out the individual vertebral levels using then ResNext 50 and those individual vertebral levels, as well as the supervised learning they're getting from the disc level grading. They were now able to build a computer vision algorithm to automatically grade the individual discs, something they were able to do relatively simply, because they started with all the information at their fingertips, and they worked with the radiologist to label the images, as well as to tackle a problem which they needed help with, and that was solvable. And I think that's really the key. And so I want to end with a quote that's, no one's really sure who said it, but I think it's really true, is that AI will not replace radiologists. Radiologists who use AI will replace radiologists who don't. Thank you.
Thank you, Michael. We have time for just a couple of quick questions.
Very nice presentation. Thank you very much. Full disclosure, I'm a radiologist also, and I do deep learning also. The points you made on ChexNet and the Stanford study were, pretty well known. A lot of people, myself, Saurabh Yah, and as well as Luke Oakton-Rader has discussed the problems with the chest X-ray 14 data set from the NIH, which ChestNet was based on, as well as the relatively weak NLP labeling. A lot of people are going through that, and redoing it. And of course, the deep radiology net, from deep radiology is kind of a joke, as most of us know. The issue being is that I was gonna give you a hard time about that, but you wisely put in that AI will be used by radiologists to replace radiologists who don't use AI, and I think that that's pretty common. The opportunities that exist in imaging and healthcare are falling nicely into these workflow solutions, which you touched on, and segmentation and classification algorithms tied into EHR that promote faster workflow. And in fact, some very interesting recent publications by Peter Cheng out of UCLA, I believe, and also that was on brain bleeds, and I think replicated by the MGH team. And then also the pneumothorax detection by Andrew Taylor out at UCSF. So these things are starting to come around, but they're binary classification problems, instead of multi-class classification, which is what Jeff Hinton and, Andrew Ng, was talking about years ago. So maybe the take-home point is that the opportunity is for binary classification algorithms for one particular pathology to address one particular pain point. And I think that that's one of the things that the ACR DSI has put out in their recent list of, areas in AI that need help. But multi-class classification problems to replace radiologists, I think, are pretty well understood to be good luck.
Right. Yeah, so I would agree with that completely, right? I think that what we're finding now is that when we have specific problems, which radiologists have, that's where AI is going to be really helpful in saying, okay, we have one specific issue, which we're trying to identify one thing, and we have all this data about that. And even then, it's being tempered by the idea of, is this solvable with AI? It's not just everything that doesn't work. We can work, if we choose specific problems for which AI is a great solution, we're going to get great results. And I think knowing those problems is, I think, the key to helping radiology and artificial intelligence.
One more quick question.
Pleasure having lunch with you yesterday, by the way.
Yeah.
Your phrase, radiologists who use AI. This is going to become a common theme for a lot of different professions. X who use AI are going to become better. Have you been able to forecast what will that enable them to do? Be more accurate? Sit back more? Will they be less intelligent in the future because they're relying on computers, like a pilot in an airplane? What do you think the radiologists of the future who use AI are going to be different from today in terms of what's going on in their brain?
So I think a big thing we have in the hospital is talking about working at the top of your license, working at your most efficient level. So a big part of radiology is measuring the area of, or measuring the diameter or the area or the volume of, let's say, masses. That is a waste of time. It's literally drawing a ruler and then measuring the volume of something. Stuff like that AI can, get rid of. So it's getting rid of those menial tasks, which they have to do, but honestly, isn't really that complicated. Anyone who can do with just a little knowledge can do those tasks. And I think that's really where the value add will start. And so they're really working on only the hard cases, the things where it's not so simple what's actually happening over here. So I think, in fact, they'll probably even have to be smarter than they were before because they're only dealing with the difficult cases, and all the easy stuff is going to be done by the artificial intelligence algorithms.
All right, thanks again.
Thank you.